In this video, we're going to see a second example of integration by trigonometric substitution. But there's a couple things that are going to change, and the first of them is that this is an indefinite integral. The previous one was a definite integral, and that we saw that there was a way to change limits of integration. Now, actually, an indefinite integral turns out to be a little bit harder for reasons we're going to get into in a moment. And the second thing I really want to focus in on is how do we choose? How do we make the choice? How do we articulate a strategy for what substitution to make? Now, what we have here is 1 over x squared plus 4 all squared. Now, one of the things I want to remind you about is that we have these Pythagorean identities. The sine squared plus cos squared is 1. If you divide out by cos squared, you get tan squared plus 1 is secant squared. And there's a third one, but we actually usually never need to use it for trigonometric substitution. These two are enough. Now, how do I know which of these I'm supposed to use? Notice how I have x squared plus 4. Okay, that's not exactly as nice as x squared plus 1. There's that 4 there. We're going to have to figure out how to deal with it. But if I look down here at the examples, I do see then one that says tan squared plus 1. As in, if I made my x equal to tangent, it'd look like something squared plus some positive value. So I kind of feel like the bottom one might work out. If I look at the top one, it would always be like 1 minus sine squared or 1 minus cosine. The sign doesn't work out. And the other thing to decide on, I've decided on using the second equation, is, well, it's not plus 1, it's plus 4 here. But what if I do the following? What if I set x is equal to twice tangent of theta? When you square the x, you get 4 tangent of theta. There's a 4 where the x is going to be, and there's a plus 4. The 4's can come out, and then it's just going to leave behind tan squared plus 1. So that's how I sort of anticipate. That's how I think forward to what is a good substitution to make. I want to decide which of these different equations to use. And I'll use the one that's compatible with the signs, like the pluses or the minuses. And then I make the coefficient adjusted to whatever I need that to be. Okay. If that is my x, then my dx is just the derivative of this. So 2 secant squared of theta d theta. Now, I have put up here the graph of tangent of theta. Now, tangent of theta is a periodic function, so it repeats many times. And if I ask, for example, if tan theta is equal to a value like, say, 1, what value of theta is that? Well, the answer is there's infinitely many. So as I did previously, I want to make a so-called restriction of the domain. I want to choose one of these branches that is 1 to 1. And if I select this green region here, between the minus pi over 2 and the pi over 2, it hits every possible value that tan could hit between minus infinity to infinity, and it hits it exactly once. There's no repeats. So I'm going to make that an additional restriction. I'm going to demand that my value of theta is between minus pi over 2 and pi over 2. Now, this choice, this analysis of what substitution I should do, the choice of making it the 2, the restriction on the domain, all of that, we sort of came up with it thinking about what would be reasonable. But if you want to, you can always go to this chart that I've shown previously. And in this chart, you can see that, well, we had an x squared plus 4. So that looks most similar to the a squared plus x. And it tells you what the substitution is and tells you what the restriction. Although, myself, I think it's better to think it through. Anticipate the trigonometric identity you're going to use. Think about what the domain ought to be. Nevertheless, we have this substitution. And so let's go and use it. Let's plug these values into it. So what do I get? On the top is the 2 secant squared of theta d theta. That's what my dx became. On the bottom, 2 tangent of theta all squared plus 4, and then all squared. Okay, I can do some stuff. I'm going to pull out all of my constants, and for that tan squared plus 1 that remains when I factor out the 4, the tan squared plus 1, I'm going to go and use my identity, and I'm going to put in secant squared. So what do I get? 2 over 16, the secant squared on the top, and then I get a secant to the power of 4 on the bottom. Secant squared and then squared again and secant to the 4th. All right, this is just a trig integral. So let's just solve it like it's a trig identical. It's 1/8, and then that looks like the integral of 1 over secant squared. 1 over secant squared is just the same thing as cosine of squared. Cosine of squared we can use the half angle identity on. That's going to look like this. It's going to be a 1/2, 1 plus rather, cosine of 2 theta. And then I can integrate that, the 1/8 out the front, the 1/2 goes to a theta over a half, and the cos 2 theta is going to go to 1/2 sine 2 theta plus c. Now, are we done? Well, not quite, because the original integral was in terms of x, correct? But now we have an integral in terms of theta. So what we really want to do is transform this from thetas back into x's. Now, before I go and do this substitution back, I'm going to take one quick look at the sine 2 theta term here, and I'm just going to apply one trig identity. I'll tell you why I'm doing this in a moment. It's just going to make my life a little bit easier. I'm going to apply something called the double angle identity. It says sine 2 theta is twice sine theta cos theta. So I've just taken this little pink portion and I've done a trig identity. I just wanted sine of theta by itself and cos of theta by itself. I didn't want to have to mess around with this multiplication by 2, this sine of 2 theta nonsense. Nonetheless, how do we take this integral, and we're going to focus on transforming it back in terms of x. Now, our substitution was x is twice tangent of theta. And so you might think if I want to go the other way around, I should just take arctangent, and that gives me that theta is arctangent of x over 2. This is fine. This is okay. Indeed, and for the theta that we have up there, we might actually just want to go and plug this in directly. In place of the theta, it's the arctan of x over 2. But when I have something like sine of arctangent or cosine of arctangent, I feel like we can do better than just plugging in the arctangent. I want to go and try to evaluate that in sort of nice polynomials and square roots and things that I understand a little bit better. Sine of arctangent, I don't know what that is. So how can I do this? Well, if I say x is equal to twice tangent theta, another way to write that is x over 2 is tangent of theta. Well, this sets up a triangle. Remember, this is indeed trigonometry. So I'm going to make a triangle. It's going to have an angle of theta, and its tangent is going to be x divided by 2. So in other words, if I set its opposite to be x, its adjacent to be 2, tangent of theta would be x over 2. And then the hypotenuse by Pythagoras is going to be the square root of the 2 squared plus the x squared. So now I know everything I could care to know about this particular triangle. I can figure out sine of theta. Sine of theta is just going to be the x over the square root of 2 squared plus x squared. In other words, opposite over hypotenuse. I can do cosine of theta. That's going to be the adjacent over the hypotenuse. As soon as I wrote down that triangle, I could figure out everything else. Now, if I go all the way back to my original equation that's written in terms of theta, now I know what sine of theta is. Now I know what cosine of theta is. And the theta that's stuck out the front, I can just put in the arctan. So plug in all of these different things inside of it. What do I get? I'm going to get the 1/16th, the arctangent of the x over 2, and then the twice, and I multiply the two different expressions for sine and cosine, and I get 4x divided out by 4 plus x squared. And then the all-important plus c, because it's an indefinite integral. So when it's an indefinite integral, there's this little bit of an extra step that you have to go through. There's a bit more of a rigmarole. You can't just choose what the values of theta are going to be and put that into your limits of integration and plug the numbers in. You get this final answer in terms of theta, and you use triangles to convert it back into answers in terms of x.